All right, in this section we're going to look at volumes of solids, and the volume of a solid of a known integrable cross-section with an area A of x from x equals a to x equals b is the integral of a from a to b, and it looks like this guy right here where the volume is equal to the area of the cross-section integrated over a specific interval. And this is really where you get to see some really interesting and fun applications of the integral. Okay, and so to find the volume of a solid, what we're going to do is we're going to slice that guy like you would lay a pineapple down and just slice right through that pineapple. And what we're going to do is we're going to sketch the solid and what a cross section would look like. We would find our area formula, find where we're going to integrate it from, and then we would integrate it over that length. And working with these guys can be a little bit tricky sometimes depending on exactly what you're looking at, but the solid shapes that you can investigate now can be shapes with very curvy, irregular looking edges, and we can look at these things now and we can find a specific volume for them. So these are really going to be fun to work with. Okay, so we've got a pyramid 3 meters high that has a congruent triangular sides and a square base that is 3 meters on each side. Each cross section of the pyramid parallel to the base is a square. Find the volume of the pyramid. So the first thing that we want to do is we want to sketch out what the solid looks like. Well, let's go ahead and see if we can't do that. If we're on the x and y axis here, basically we've got here's the x axis, or here's x, here's y, and it says that we've got this pyramid shape coming out. So we've got this guy that's kind of coming out, and he's shaped like a pyramid, and I'll see if I can make a good pyramid shape here. That's not too bad. And here's an edge here, and there's an edge in the back. Okay, so we've got this pyramid shape, and what we're going to do is we're going to just make a slice right down the middle of that thing. We're just going to take a shear plane, and we're just going to slice it right down any part of the pyramid. And when we do that, I'll get us a better line here. We're going to make it just a clean cut right here. What we're looking at is a square. That blue line, when it cuts through that red pyramid, gives us a square. And we're told that the pyramid is 3 meters high. So when we come out on that x-axis, we're only coming out to 3. And we're told that it's a square with a base of 3. So then each of these sides is also a 3. So when we're looking at this area of the cross section, we're looking at a square that has a length of 3 for each side. So we just want to find the volume of the pyramid. Well, what we need to do is find the volume, find the area of this side. And how would we do that? Well, if we let each 3 be represented by a variable x, because we're looking at a pyramid whose sides are always changing. Okay, but we know at the bottom, at the base, we've got a 3 square unit area. And so how do I find the area of a square? I square the sides. And our limits of integration then are from 0 to 3. So we're going to go from 0 to 3. And we're told that because we're told that it's 3 meters high. And so we know that we're going to have the tip on the origin. We know that we're going to go out to 3 on the x-axis. And so what we need to do then is we'll just integrate from 0 to 3 the area of the cross section, which in this case is a square. So x squared dx. That's it. That's all there is to it. And when we integrate this, we're going to get x cubed over 3 evaluated from 0 to 3. And if you want to punch this in on your calculator, you are more than welcome to do so. You should get the same exact number that I'm going to get. 3 cubed is 27 divided by 3 plus 0 divided by 3 gives us a volume of 9 meters cubed. And so that's how you can do that. Even, and this is a pyramid. This is a regular shape for us, something that we're used to and have seen before. So what happens then if you get something that has a different shape? Well, let's look. How about this? The region between the graph of f of x equals 2 plus x cosine x and the x-axis over the interval from -2 to 2, and we revolve it around the x-axis to generate a solid. Find the volume of the solid. Well, now what we're going to do is take this shape right here and see if I can highlight it very well. I don't know. This area right here, this part of this curve. We're going to take this part of this curve right here, and I'm going to trace it. And what we're going to do is take this shape and we're going to rotate it around the x-axis. And when we do that, I'm going to get this kind of a shape right here. So now I've got this shape with this extra area added in. And so this is what we're looking at. Kind of looks like a vase on its side. Okay, kind of looks like a vase on its side, or a fish without a nose. But what you're going to do is we're going to rotate this guy around the x-axis. And when we do that, we're going to get a circle shape cross-section. A circle-shaped cross-section all the way around. And it doesn't matter where you look at your slice, and we'll use a red slice here. If I draw that slice anywhere, what I'm going to end up with is a circle. Now, the question is how to use it. Well, the area of the circle is pi r squared. So what's the radius for the circle? How far from the center to the circle? How far from the center to a point on the circle? Well, it changes all the time, but it follows this pattern right here. Okay, no matter where I'm at from -2 to 2, the furthest I am from the circle is 2 plus x cosine x. So when I set this integral up, then I'm just going to integrate, and I already know what I'm integrating from. I'm integrating from -2 to 2. Of 2 plus x cosine x. And when you do this, there's a lot of different ways you could do this by hand. Integration by parts is probably how you would have to end up solving it eventually. What I would recommend is if you know how to integrate by hand, use your calculator to help you now. And you can punch it in. It doesn't take any time at all, and it's going to end up giving you 52.43 units cubed. And that's the area of this shape right here. And what I think is really interesting is it doesn't matter that those lines aren't straight. Once we revolve it around and we know the shape of the cross section, then the rest is definitely a lot easier than you think. But what about something a little bit different? So let's say we've got a washer cross section now, or a ring cross section. It's still the same thing, but we're looking for the area then of the actual washer part. So we're looking for the area of this part right here. Okay, we're looking for that area in there. And how do you do that? Well, you have to find the area of the big minus the area of the little, and that's this integral right here. Okay, so it's still the same exact thing. We have to find the area of that cross section and the points that we're going to integrate from. And once we know those things, then we can get a graph. And once we've got that graph, then we can set our integral. And once we set our integral, we can use our calculator to do it by hand. So we're going to look at the region in the first quadrant enclosed by the y-axis, right here, the y-axis, and the graphs of y equals cosine x and y equals sine x. So we're looking at this area right here. So let me clone this guy and flip him. And what we're going to do is when you revolve it around the x-axis, you're going to get this shape right here. We're going to revolve it around the x-axis. And when we do, you get this bigger circle, and then you also get a little circle. And the part then that we're interested in is this shaded in part right here. We're looking for this kind of triangular looking slice. But once we take our knife and we slice through this circle with a, just like we were cutting a piece of fruit, I'll put a blue line in here. We're going to slice on this blue line right here. Once you slice on that blue line, you're going to get a shape that looks like this guy right here. And so we just need to know what that outer radius is. What's that big radius on this guy? Well, the big radius is going to be cosine squared, or is going to be cosine x. That's your big radius. Your little radius is going to be sine x. And you can tell that by either looking at the graph or just kind of remembering how things go. Either way. And so what we'll do is we'll set up our integral. And we just need to figure out what this point is right here, because that's where our integral will stop. So I know I'm starting at 0. I don't know where I'm stopping, but I do know that I've got the big radius, so pi times the radius squared, the big radius cosine squared x, minus pi times the little radius sine squared x dx. Okay, now I just got to figure out that stopping point. Well, how can you do that? Remember that if you set sine x equal to cosine x, it will give you that value where they are the same. And if you're familiar with your trig, then you can remember that that these two guys right here will intersect when x is equal to pi over 4. Okay, remember at pi over 4, square root of 2 over 2, and the square root of 2 over 2, those are the same. So you can look on your unit circle, you can look on a trig chart, but you want to find where the sine x and the cosine x are the exact same, what radian measure that is, and it's going to be pi over 4. Now there's several different ways that you can solve this. That pi can actually be factored out. And so I'm looking at the integral from 0 to pi over 4 of cosine squared x minus sine squared x. And you can use a trig identity to help you solve this guy down. Or you can use your calculator. Now you have to read the directions, because if they tell you to find the exact amount, then we've got to be able to do that. And so if we're using our trig identity, if you remember those at all, cosine squared x minus sine squared x is cosine 2x. And you can make a u substitution here and integrate So we would let u equal 2x. And so du is going to be equal to 2 dx. So 1/2 du is equal to dx. All right. And so when you make your u substitution, you're actually going to be integrating times pi 0 to pi over 4. I'm starting to run out of space. You're actually integrating then 1/2 cosine u. Well, that's not too bad to do. Move over here to this side. When you do that, that's going to be pi over 2. And then when you integrate, that's going to end up being sine u, sine u, sine u, sine 2x. Okay? And we're going to go from 0 to pi over 4. And so when you do that, you're going to have pi over 2 times the sine of pi over 2 minus the sine of 0. And that's going to give you then pi over 2 units cubed for your area, for that highlighted region. If you punch it into your calculator, pi over 2, you're going to end up with a decimal. So it won't be exact, and that's why you need to know what your directions say. But pi over 2 in decimal form is 1.5708. Units cubed. That you can find volumes of things is by using shells, and shells can be a little bit tricky because sometimes they don't rotate the way we think they should, and so you have to really pay attention when you're working with a shell to make sure that you've set your problem up correctly. Okay, so let's take the region bounded by the curve y equals, how about the square root of x? And we're going to look at a region that also has a lower boundary of the x-axis. And we're going to rotate around at the line x equals 4. Okay. Let's see. Let me back that up. We're going to stop it at 4. We're going to stop at x equals 4. So we're going to be bounded by y equals the square root of x, y equals the x-axis, and the line x equals 4. Okay, these are our bounds. And we're going to rotate around the x-axis. Okay, so let's look at what's going on here. Square root of x, that's not a hard problem. So we've got this guy right here. Square root of x is going to come out and look something like this. Okay, we're going to rotate this way around the x-axis. So what that's going to do is give us a shape. It's going to give us this shape right here. But what we're going to do, well, let's see, and we're stopping at, let's add this guy, 4. Okay, so the area we're interested in is this shaded region right in here. Okay, but with a shell, it's a little bit different than what we've looked at so far. What we want to do is we want to look at 2 pi times the shell radius. And so on this particular one with the shell radius, we're wanting to look at slices going horizontally. So we want to look at this slice right here, okay? And we're going to actually look at how this guy rotates around and we're going to add up all of those little guys right here. So this is actually going to be a dy, a change in y is what we're looking at. All right, and so what we need to know is we need to know the shell radius and the shell height. Okay, those are two very important things. And so the shell radius then is going to be the distance we are from the center of the shell to the edge of the shell. So remember, here's the y-axis here, and so this radius from here to here, okay, that radius from there to there, the radius from here to here, okay, these different radiuses, all right, so in this case, those are all going to be y. Okay, the shell radius equals y. Okay. And then we look at the shell height. Okay, now we look at the shell height. And so we've got this equation over here that says y equals the square root of x. Well, now that we're going to have to work with an integral with dy in it, then I've got to make sure that I have an equation that says x equals. So what I'm going to do is take y equals the square root of x. I'm going to square both sides. And so y squared equals x. Okay. And so my shell height then is going to be what? Well, I go all the way over here to 4. Remember, this is 4 right here. And my height then is going to go up to my graph and stop. Okay, so this is my height, this purple line. Well, how tall am I at that purple line? Well, the y squared is the line, is that red line. But I don't use all of y squared. I'm only using the 4 minus y squared part of that. Okay, so my shell height is going to be 4 minus y squared. All right. Now, and then the last thing I have to do is I have to figure out what this point is right here that I stop. Now, I know the x-coordinate is 4. So when the x-coordinate is 4, what's the y-coordinate? It's going to be a 2. Okay, so when I integrate this guy, I integrate from 0 to 2. So this integral is going to look like from 0 to 2, okay, 2 times pi times the shell radius, which is going to be y, times the shell height, which is going to be 4 minus y squared, times dy. So one thing to kind of keep in mind is if we're revolving around the x-axis, we're going to look like this, which is what we're doing right now. If we revolve around the y-axis, we would look like something that we're a little bit more comfortable with. So this is a little bit more challenging for us to think this way because we're just not used to working with y, with equations that say read off as x equals like this guy right here. We're just not quite as familiar. But integrating it now is not a problem. You can do it by hand. You could do it by calculator, you know, whatever your fancy is. So, you know, if we did it by hand, this is 2 pi from 0 to 2 of 4y minus y cubed. Okay. And so when you look at this, this is going to be 4y squared over 2 minus y to the 4th over 4 times 2 pi from 0 to 2. And when you stick 0 into here, you're not going to get anything out because it's going to put 0 in the numerator on both. So what I have is 2 pi times 4 times 2 squared over 2 minus 2 to the 4th over 4. And when you simplify all that mess down, you end up with 8 pi. If you put it into your calculator, you would end up with 8 times pi, which is what I just said. And 8 pi is 25.1327. And so that's how you work with discs, washers, and shells.